Where's my mouse? The very last thing that we talked about last time was I wrote down an equation separating out the external, yeah, that's for homework, the external and the internal works done in the work energy theorem. So what we had was that work 1 plus work 2 plus ... where these are external, or oh, I'll do that in a minute, equals the change in kinetic energy minus work 1 plus work 2. These are different works now, where these are conservative, minus work 1 plus work 2 plus ... These are non-conservative. And so these over here, these works are the works done by external forces, and these works are the works done by internal forces. So that was just a rearranging that I wrote down and I told you would be useful later, and it will be useful today. So I want to remind you guys that conservative forces, as far as we've seen, and actually by definition, conservative forces only care about the initial and final positions when you calculate work. So for example, gravity is a conservative force. The only thing that the work cares about, like the work done on an object, is where did the object start and where did the object finish. It doesn't care how it got from point A to point B. It only cares about where the starting and ending places were. And so we can actually use that notion to define something that is internal to the system. So what we are going to do is we are going to define potential energy as a quantity of energy, just like how kinetic energy is a quantity of energy. It's a quantity of energy that a system possesses due to its position. Or due to the position of or due to the relative position of objects within the system. So, for example, the potential energy in for a spring is totally well defined because the work done by a spring internal to the system only depends on how stretched the spring is, i.e., where is the object that's attached to the spring. So the change of that quantity, that potential energy, is the negative of the work done by the conservative force. So if you have a conservative force, its work, the work that it does only depends on the position. And so it makes sense that depending on the position that an object is in, when it goes from position A to position B, its energy will change in a predictable way. And so what we're doing is we're actually taking this term and we're calling that potential energy. So we define, or so we can write, the change in potential energy is just defined to be potential energy at B minus the potential energy at A. But we know how much that should change by. If the potential energy is associated with conservative force, then that change in potential energy is precisely the amount that it's precisely the negative of the work that force would do. It's the negative of the work done from A to B of that conservative force. So this is to say, and by the way, the reason why it makes sense to call it the negative is because if you put it back on the other side, then when the potential energy goes down, then the kinetic energy goes up. Or assuming that there's only the two things happening there. Basically, we expect there to be a finite amount of this stuff, and so if one of them goes up, the other one goes down. That's why we define it as the negative of the work, because if it was the positive of the work, then the delta wouldn't make a whole lot of sense, and this equation wouldn't be particularly useful. Oops. But you'll see this in more detail as we go. So just as a side note, there is a form of potential energy for every conservative force. So potential energy is just a number that's associated with a place, right? Like, for example, this pen has some gravitational potential energy because of its place. It has a different potential energy because of its place here, has a different potential energy here and here and here and so on. So it's a function of position. And every conservative force has a form or has a potential energy function. There's a form of potential energy, which is often abbreviated PE, for every conservative force, not just gravity. And that's just because if you can associate a number with a position, then you can find the difference in those numbers, and that should give you the, and because the work only depends on a change in position, you can relate that change in position, that difference of potential energy numbers, to the work done. No, we're going to get to that. So in particular, precisely to answer your question, it does not make sense, and in fact, we cannot define potential energy for non-conservative forces. And the reason for that is that the potential energy, a potential energy should be a function of a location, right? You plug in a position, it gives you a number. But we know that for non-conservative forces, if you go in a loop, you don't necessarily come back out with the same, or you don't going in a loop doesn't necessarily mean that the work that that force does is zero. So that would mean that somehow the energy would have to change, would have to change even though your position didn't change. And you guys should know that like f of x, where x is the position and f is the potential energy, f of x minus f of x is zero. It can't be non-zero. No, potential energy isn't potential. Well, so yes, it is true that if there's a potential energy associated with the force, then the force is conservative, and vice versa. That is true. So we'll talk about this in a little bit more detail, this potential energy notion, but first we just got to go over one more thing so we can finish up this notion of this rearrangement of the work energy theorem. So we know that we can capture these works done by a change in potential energy by delta PE, right? So there's still some works that we still need to handle. These are the internal non-conservative forces, but we can handle those too. So the work done by non-conservative forces, well, we can't write it as a potential energy, but we can write it as something else. Non-conservative internal forces, I should say, can also be accounted for. They just can't be called potential energy because potential energies have a particular property. We call the work done by non-conservative internal forces, we call this thermal energy. So, and it's not always thermal energy, but in the cases that we're going to see in this course, it will be. So we define the change in thermal energy of a system, E sub TH for thermal, is the negative of the work done by the non-conservative forces. So it's just like potential energy, except potential energy is associated with conservative forces. It's the work done by conservative forces. Thermal energy is associated with the work done by non-conservative forces. And so putting this all together, these new names, and by the way, all we've really done is just name what these works mean, what these works are. We get the following. We get that the external work, the total external work on the left-hand side, total external work, is equal to a change in kinetic energy. That's still there. God, I can't write. Hands are shaking. Something, something, mom spaghetti. Plus, then there's a whole bunch of potential energy terms, right? And we're going to lump them all together. We'll call it delta PE total. There could be more than one. Yeah, needs to be. Yeah, there you go. There could be more than one potential energy term. There could be, say, gravity and a spring. And so you would just have two potential energy functions, and those would be added together to give you this change in the total potential energy. And then we have plus the change in thermal energy. And this equation here is a super important one. That is our final form of the work energy theorem. And the reason why we break it up this way is because potential energy makes if you know the potential energy of a system, it makes the problem very, very easy to analyze. You don't have to do any integrals anymore. So we've already talked about this notion of a system. Oh, did my internet connection die? Oh, okay. Okay. I may have just been memed on. That's okay. Right. So so now let's suppose So remember, external means external to the system that we're considering. And then these are energies associated, those are energies internal to the system we're considering. So now what happens if everything is in our system? What if our system is everything? And by everything, I mean the entire universe. Well, then there's nothing external, right? There just can't be, because there's nothing outside of everything. In that case, the work energy theorem becomes this equation. 0, because there's no external work, equals the change in kinetic energy plus the change in potential energy plus the change in thermal energy. And so this is the classic energy conservation law. Now, just to be clear, there can be simultaneous changes in multiple potential energies and multiple thermal energies. For example, let's say that you have two objects, both of which have separate, unrelated, non-conservative forces acting on them. Then you'll have a change in thermal energy of one of them, and you'll have the change in thermal energy of the other one. And they could both be increasing, one could be decreasing, one could be increasing, they could both be decreasing, whatever. But the point is you can have multiple different energies that are all added together. And so it's really not just 3 terms. In general, it'll be however many terms have to be there. Often for this course, there won't be more than 5 terms at most. Like there might be 2 potential energies, and there might be 2 kinetic energies, and there might be 1 thermal energy or something like that. For example, if your system has 2 separate things moving at different speeds, then there will be 2 changes in kinetic energy, because one object might be changing its speed more than the other object, and so on. But these encapsulate all of those types of energy. So when I write delta KE, I mean the change in the total kinetic energy of the system, meaning you add up the kinetic energy of each object, and then you calculate the change in that total. Same for potential energy. You find the potential energy from every single conservative force, add them all up, and then find the change in that thing. And then the same for thermal energy. So let's just look at by the way, an example where there might be more than one potential energy would be like, let's say you have a spring pointing upwards, and then there's like a ball resting on it, right? If the ball is oscillating, there's gravity that's acting on it. That's a conservative force, which we could consider having a potential energy. And then there's also the spring potential energy, the energy associated with the spring force. So in that case, there'd be 2 delta PEs. So that's just one example. And in fact, a question like that shows up on the homework. So, keep that in mind. Now, there's one more renaming I would like to do. So far, all we've done is just rename things in the work energy theorem. We've just grouped things and renamed things and so on. But there's one more renaming. So note that, and this should account with, or this should agree with your intuition. Potential energy and kinetic energy can be exchanged with each other. At least sometimes they can. But kinetic energy and thermal energy can't. And also it's true that like you can't exchange thermal energy for potential energy back and forth. So instead of having kinetic energy and potential energy, we just come up with this new thing, call it mechanical energy, ME, which is just the sum of the potential energy and the kinetic energy. This we call mechanical energy. So the reason why we do this and why you can't do it for thermal energy is because, in a sense, thermal energy is like a one-way ticket. Once you turn, you can always turn kinetic energy or potential energy into thermal energy. What you cannot do is then turn it back. Like think of friction, for example. If you rub 2 things together, you can't unrub them to get that energy back, right? Like the things will just heat up, hence the name thermal energy. And you can't get that back without putting in more energy elsewhere. And in fact, in 9B, you guys will see this when you talk about thermodynamics. But this is just a general property. And it's because thermal energies come from non-conservative forces. You can't undo the path. Thermal or non-conservative forces always take away energy from the system, assuming that they're doing work. And so you can't undo that, because if you go back the other way, like in the friction example we did last time, you just lose more energy. So all of the above stuff that we've talked about, like this equation in particular, this equation, all of those equations, all of this notion of being able to exchange potential and kinetic energy, all of this is known as a conservation principle. conservation principle. So a conservation principle kind of is, as the name is, so you can't exchange potential energy and thermal energy freely either. Let me put this. There we go. So let's talk about what a conserved quantity is, because you guys might not know what that is. So a conserved quantity, this is like a number that's conserved, or a vector that's conserved, is a quantity that doesn't change over time. It stays the same. It's conserved. And so what this is saying, for example, in this example where where our system is everything, what this is saying is if one of these things goes up, if say the kinetic energy of the system goes up, then the potential energy or the thermal energy has to go down. And so what we're doing when we say it's conserved is we're saying this total thing, kinetic energy plus potential energy plus thermal energy, that total thing is conserved. I.e., if one of them goes up, the other one has to go down. And that's accounted for because the changes have to add up to 0. And so the reason why we call this a conservation principle, or the reason why we called conservative forces conservative, is because they tend to lend themselves well to conservative or to conservation principles. And indeed, we'll find that if it's true that the change in thermal energy is 0, then it's really conservative, meaning that no matter what you do to the system, the total observed energy doesn't change. But that's just a historical quirk that it was named that way. So there are some useful submodels of this notion of energy conservation. By the way, I didn't actually write this down, but this is energy conservation is what we're talking about here. You have the total energy, kinetic energy, potential energy, and thermal energy of a system. And so long as there's no extra energy coming into the system via work, as long as the external work is 0, then those things have to change so that the total change, so that the total amount of those things is always the same. If one goes up, the other one has to go down. If delta KE is positive, delta PE or delta E thermal have to be negative, just to make sure that the total number is the same. And this result, all it comes from is it comes from this notion of work. It just comes from Newton's laws. Remember, the way that we came up with the work energy theorem, which is what this is a statement of, is we just started out by writing Newton's laws and then asking what happened, or how does the speed change if if we don't care about how the direction changes, right? So energy conservation is a consequence of Newton's laws, something that's lost on a lot of students that I think is useful for you guys to think about. Right, so there are some useful submodels of energy conservation. So when I say submodels, I mean like a set of ideas that kind of make that give you specifics about how the energy is conserved. So one submodel that you might come into are systems with no drag or friction. So when that happens, well, as far as you guys know, those are the only non-conservative forces. And so that would mean that the change in thermal energy is 0 because there are no non-conservative forces. And so that means that our energy conservation equation, assuming the external work is 0, is 0 equals delta KE plus delta PE. That is, mechanical energy is conserved. Again, this is all assuming there's no external work. I.e., the total mechanical energy of the system doesn't change. Another useful submodel is the notion of two things colliding elastically, or undergoing an elastic collision. What this means is that there's no change in thermal energy and there's no change in potential energy. So again, in that case, our 0 external work potential or energy conservation equation becomes 0 equals the change in kinetic energy, which just means that the kinetic energy is conserved in an elastic collision. And we'll see examples of that going forward once we talk about momentum conservation, but this is just a sub-model. It's just a box that you can put around a specific type or a specific concept, the notion of two things bouncing off each other elastically, you can associate that concept with these notions. Right. So I've talked about this notion of potential energy already. I just said it's the negative of the work done by the conservative force, but I haven't actually told you what it is. So let's actually go and work out what the potential energy function is for gravity. Remember, it's a function because it depends on a position in space. You plug in a number and it outputs, or you plug in a place and it outputs a number. So let's talk about the potential energy function for gravity, and then we'll do the same for the spring as well. So the reason why we want to know what this potential energy function is because we could compute it by just doing the line integral and then just sticking a negative sign in front. And we could do that every time, but it'd be kind of annoying because you don't need to, like, as long as you know what the number is at every place, at every location, like relative to the Earth, say, let's say that you knew the potential energy value of the gravitational potential energy value at every place at every place around the Earth. Well, then you could just take the difference to find the change in potential energy rather than having to do a line integral every time. So that's what we're going to do, because it's generally easier to just take the difference of two numbers than it is to actually compute the work done by the force every time. So just as a quick reminder, I want you guys to remember that the work done by gravity, we've already shown this to be the case, from position A to position B, this is negative mg delta y, where delta y is the change, it's the height at position B minus the height at position A. So because the change in potential energy is the negative of the work done by that gravitational force, we have that the potential energy due to gravity, the change in potential energy due to gravity should just be mg delta y. So then the question is, what should potential energy be? So this is the change in potential energy between 2 points, right? Between points A and B. So what should the potential energy be? Because we would want to be able to compute the potential energy at point B, compute the potential energy at point A, and then just take the difference to get the change in potential energy between points A and B. So we know that the mass and the g part, those are just the same. Those are just numbers. They're not changing at all. So they're not contributing to the change in potential energy. So let me just write words. We want to know what potential energy due to gravity as a function of height b. And so the m and the g aren't changing. So it's not like, so what am I trying to say? We're kind of trying to cancel out these deltas, but it's just like how with derivatives, you can't just cancel out a derivative. Like if I wrote d by dt of the potential energy due to gravity equals mg d by dt y, you couldn't really cancel these out. You'd have to be a little bit more careful. However, in this case, it does actually just work out relatively easily that we can cancel them out because mg is a constant. They just don't, m and g don't change with position. So the end result of this notion of canceling out the delta is that the potential energy due to gravity at a position y is mgy. And so we can just check if that is the correct potential energy. Now what happens if we take the difference between two potential energies at two different places? Then we would end up with that the change in potential energy due to gravity is mg delta y, because you could factor out the mg, right? It would be mg yb minus mg ya, and so this becomes mg yb minus ya, which is mg delta y, right? So that's why that's a way to check that this potential energy works. But we got to be a little bit slower here, because this isn't the only correct thing that works for the potential energy due to gravity. What if instead I had told you that the potential energy due to gravity as a function of y was mgy plus u naught? It's capital U, where u naught in this case, it's just a number. It's more than a number. It's a number with units of joules. So then, if that's the case, we can go and ask what the potential energy due to gravity, the change in the potential energy would be if this was the correct thing. We can check it against what we know it should be, but we would find that the change in potential energy would again also be mg delta y. So what gives? Like why is it that that we could have just added some random number, whatever that number is, to our potential energy function, and it still works. It still matches the potential energy, or what we know the potential energy should change by. Well, the point is the potential energy at a particular place isn't so important. The important thing is what the potential energy is or what the difference in potential energies is between two places. And so as long as you're adding the same constant to both potential energy or to both places, then that's safe, because then the change in the potential energy doesn't care. You just add u naught on one side and you subtract u naught on the other. And so you can always add a constant to a potential energy function. So let me write this out just to be a little bit more explicit. The example here, by the way, is this u naught really characterizes where is the potential energy 0. So imagine that I said that y equals 0 on the floor, right? Well, what makes the floor the right place to put y equals 0? What if I instead had chosen y equals 0 on the roof, right? Well, all that would account for is that would just account for a change in coordinates. It would just be mg y minus, say, y naught, where y naught is the location of the reference point of where I'm calling y equals 0. And so this u naught, that just lets you pick wherever you want the potential energy to be 0. For example, if I wanted the potential energy to be 0 10 feet underground, right? But I wanted to choose my y coordinate to be 0 on the floor, well, then what do I have to do? I would just have to figure out what the potential energy is 10 feet underground if it was just mgy, and then I would just subtract off that number in the form of u naught. And that would give me that the potential energy is 0 10 feet underground, and y equals 0 is still at the floor. So this is all to say that we can reference the 0 potential energy, i.e. where the potential energy is 0, to be anywhere we want. You can always choose this. This is a fact about our universe. And things still work out. I.e. the change in potential energy doesn't care. And so this choosing your reference point where the potential energy is 0, this is equivalent, and it really is the process of adding a constant. So you can always add a constant to the potential energy function. You just have to add the same constant to the potential energy function everywhere. I.e. I can't add 5 joules to the potential energy on the ground and then 8 joules to the potential energy 10 feet above the ground. It has to be the same thing that I add to my potential energy function everywhere. Yeah, this is basically what ground is, and you guys will talk about that in 9C. So this is important because it can let you solve problems that would otherwise be challenging, because you can just say, oh, well, if the potential energy is 0 by choice at one location, then you know that the total energy is, say, just the kinetic energy. And if you know what the initial kinetic energy is, then you can find out, say, what the final kinetic energy is if you know how much the potential energy changes by. So this is an important point, and I just wanted to beat it into your heads, so then you guys are familiar with it. There's discussion of this in the Libre text, by the way, which I also suggest that you take a look at. So there's an example that I go over in the lecture notes, which I'm not going to spend any time on. I'm going to do a slightly more challenging example because, why do 2 examples when 1 example do trick? So if you are curious, go look at that. Let's do another example that is slightly more complicated. So let's look at an example of a car going around a loop, a vertical loop, with no friction. So already the no friction business, the no friction business is should tip you off that we are in the case where mechanical energy is conserved. Now, so long as we choose our system to be sufficiently big, that i.e. contains sufficiently many things, then there won't be any external forces, and we can just handle it in terms of changes in kinetic energy and changes in potential energy. So the picture here is you have your car, you have your loop, or that's not your car, that's the ground. Here's the car, it's a box, so sue me. Let's call this height YA, and the car starts out, at that height, moving forward with some speed, whatever that might be. I don't even know what I referenced. My brain is so fuzzy right now. And then let's just ask how fast is the car going at some height around the loop. So let's say that the car is at this place around the loop, and it's going around. Say that it's at some height yb. Now again, using Newton's laws to solve this problem would be really challenging. I think this is somewhat like the homework problem. It's not quite like it, but it's somewhat like it. Right. So the question then is how fast is the car going at that height? So we can use energy conservation. So we're going to write down what our system is. We'll treat our system as the car plus the Earth. We want to include the Earth in our system so that the gravitational force is internal, and so we can treat it using potential energy. So in that case, because there's no friction, we have that 0. We're going to assume that let's just write this down. It's equal to the change in kinetic energy plus the change in potential energy. Now we're going to assume that the Earth's not moving here. It's a reasonable assumption. Relative to the car, the Earth isn't really moving at all. And the potential energy of the Earth does change, but it changes very, very, very minimally. So we're going to neglect that too. So here, the potential energy is just the change in potential energy of the car. So in that case, it would be mgyb, and I'm going to choose that y is, or that u naught is 0, minus mgya. Sir, scroll slower. Sorry, I got to keep going, man. And so what we have is that 0 is equal to the change in kinetic energy plus mgyb minus mgya. And ya and yb are just numbers that are maybe given to you, or maybe you have to solve for them. And then we can figure out what the change in kinetic energy is. The change in kinetic energy is just the kinetic energy subtracted from one another. So it'd be 1/2 mvb squared minus 1/2 mva squared. When there's no friction, is mechanical energy always conserved? It's only conserved when there's no external forces. In this case, there are no external forces, so long as we include the Earth in our system. There's no like somebody pushing on it or something like that. So in this case, the mechanical energy is conserved. If there are external forces, then the mechanical energy will change by however much work the external forces do. Right, so we have 1/2 mvb squared minus 1/2 mva squared, that's the change in kinetic energy, plus mgyb minus mgya. And now let's say that we were given the initial velocity, and let's say we know the change in height. We know what ya is, we know what yb is. Then we could just solve. We could solve for vb. Vb, it's going to be some complicated thing. And by the way, this is the speed. This is, remember, if I don't write this, assume it's the magnitude of the vector. So this is square root 2 over m. And by the way, this algebra is not hard, so I'm going to skip it. Times 1/2 mva squared plus mgya minus mgyb. Or rearranging it, we get that vb, or simplifying rather, we get that vb is square root of va squared minus 2g yb minus ya. And so just by plugging in a few numbers and doing algebra, we figured out how fast the car must be going at that point, or really at any height along the loop, because you could just plug in different numbers of yb and different numbers of ya and plug in different initial speeds. So hopefully you can see why this energy conservation principle is super powerful. Like if I asked you this question a week and a half ago, you would have to figure out what the acceleration is, and you'd have to figure out what the forces are in the gravitational force, and it'd be in different directions because the normal force is up and to the left and the gravitational force is downwards, and everything would be messy. And it'd be really challenging. This way, it's like 6 lines of algebra, which is really powerful. So now I'm going to show you another application of energy conservation, which is again mechanical energy conservation. This is gravitational potential energy, and kinetic energy. And then we will move on and hopefully get through the business for the elastic force. So let me change screens. I'm going to show you a demo that I would normally do in person, but I can't. This is a lovely demo by the wonderful Walter Lewin. Yeah, power series is powerful. So what he's about to do, no, I factored in a minus sign. What he's about to do is he's about to demonstrate his trust in energy conservation. What that means is he's going to take a 12-pound bowling ball, which starts off at rest with some potential energy, and then he's going to let it swing. It'll swing at the bottom of its arc. It's probably going, 20, 30 miles an hour. At the top of its arc, it's obviously 0, moving at 0 speed. And the point is if energy conservation wasn't true, if this didn't work, then the bowling ball might hit him in the face and ruin his day. So this is just a demonstration that if the kinetic energy starts off at 0, i.e. it starts off at rest, there are no external forces, and the final, if the kinetic energy starts off 0, and the change in height is 0, then the final kinetic energy is also 0. And that's just by energy conservation, right? If delta PE, if the gravitational change in potential energy is 0 because it starts and ends at the same height, then it will not be moving by the time it gets back up to that height again. So let me show you this demo.
This object an initial speed when I stand here. I trust the conservation of kinetic energy.
You have to be very careful.
I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it 0 speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0.
So he lives, and it comes very, very close to touching his chin. It doesn't exactly touch his chin.
Physics works, and I'm still alive.
It doesn't exactly touch his chin for good reasons. The ball is slowing down. There are other forces here. There are non-conservative forces at play, actually. Friction is a good example, like air resistance. Oh, I think that. Something in the Discord if you can hear me still. Okay, so you guys can hear me. Excellent. Okay, so then I'm just going to close out of Chrome and hope that you guys, I don't think that, well, okay. I guess we'll end lecture there. This is as good a time as any.
Sam, I'm sorry to disturb, but you are muted.
Yeah, good catch. Okay. I just want to go over one more thing. And so then we'll call it a day. So just quickly, I just want to introduce this notion of the, it's already 2 o'clock. Let's just end it here. Well, no, I'll go for like 5 more minutes, if only because we have so much to get through and we didn't get nearly far enough. So bear with me for just 5 more minutes. We're going to talk about real quick the potential energy for the elastic force. Right, okay. So the point is so just like gravity, for the elastic force is conservative. So we should be able to write down the potential energy for the elastic force. So let's suppose that we have a mass on a spring. A mass is on a spring. Well, in that case, we know what the force is from the spring. The elastic force is minus k times x minus x naught. Now here I'm writing out the displacement. I'm writing out the displacement explicitly. So here x is the position. It doesn't just have to be in the x direction, but it's just how it's typically written. And x naught is the equilibrium position. It's a vector that points to the equilibrium point. And so let's say if these are along the x-axis, so if everything is along the x-axis, i.e. if the vector x is x I hat, and if the vector x naught is x naught I hat, and the object is moving along the x-axis, then the work done by the spring on the mass from, say, position xa to position xb would be an integral from xa to xb of minus k times x minus x naught dx, right? This is just along the x-axis. And again, this is treated in depth in the LibreText. And so we could just do this integral. This is minus 1/2 k x minus x naught squared, sorry, xb minus x naught squared minus xa minus x naught squared. And so we can write this as minus 1/2 k delta x displacement, where x displacement is x minus x naught. It's just the absolute value. So that implies, because we can write it this way, because k is a constant, and because the potential energy is the negative of the work, that implies that the potential energy due to the elastic force as a function of x, again, this is assuming everything is in the x direction, but it generalizes, is 1/2 times k times the x displacement squared plus u naught, where again, u naught is just a constant. So if you took the difference between the potential energy at point A and point B, you would end up with this. Sorry, this should be x displacement squared here. Squared. So by convention, and yeah, we are almost done. By convention, we don't always do this, but we usually do this. We choose u naught, or we choose the 0 reference, the place where the potential energy is 0, to be at x equals x naught. That is, we choose that PE, due to the elastic force, of x naught should be equal to 0. And so that implies that 0 should be equal to 1/2 k times x minus x naught squared plus u naught. Sorry, this should be x naught minus x naught because we're plugging in x naught here for a position. And so this just implies that u naught is 0. So by choosing that the reference point, that the 0 potential energy is at x naught, this implies that u naught is 0. So that gives us that the potential energy, by convention, the potential energy due to the elastic force, assuming everything's in the x direction, is 1/2 k x minus x naught squared. And that is where we will end today. All right. Sorry.